Welcome back to Thermodynamics 1 at the University of Hartford, ME236. This is class 6. We're going to cover compressibility. Notably, this is the last class in chapter 2, and this will be the last material that gets covered on exam 1. We're going to cover compressibility factor. This is essentially a correction factor to the ideal gas law. Ideal within the ideal gas law means, obviously, that it's not reality. But for certain ranges of performance, it works pretty well. As we saw in the demo from the last class, we got pretty close to finding out that gas constant. But there are, as you start to get into large values of certain parameters, you are going to deviate. So we have this compressibility chart right here, and this is in the Appendix D in the Bornacki textbook. Interestingly, Sengel uses a different type of graph. And I'm a little bit more familiar with that one than this one. But what you'll notice along the x-axis is something called reduced pressure. And you'll also notice this TR, lines of constant TR. And these are reduced temperatures. And what we do is we take our actual pressure and divide it by the critical pressure that we can find from this table A2 in the appendix. And same thing with its temperature. And make sure we're using absolute values. So we have Kelvin. And we also have the pressure as, they're listed as megapascals. And that is also absolute pressure. They also include the molecular mass in here if you wanted that for some reason. And then there is a critical of specific volume. But we don't actually use that, I don't think, anywhere in this graph. But in the other book, Sengel, they use a... they call it like a pseudo-reduced specific volume. So that's kind of interesting, isn't it? I think so. So you go ahead and use these reduced values to try to look up what the compressibility factor is. Now this can be an exercise that you might not be used to because on the x-axis it's a log scale. So be on the lookout for that. You can also see that this thing has sort of a phase thing going on. And we have saturated gas and we have saturated liquid. So you can kind of think of this as an upside down, like a sideways dome taking place, a vapor dome. So what you're familiar with. So let's see, I could look up a little bit later, right there. So you can see that we have saturated liquid and a saturated vapor. So just be aware of those types of things. So also taking a look over here, here is where we start to have, anywhere down in here where we deviate from 1. So we could be, this factor, when it's equal to 1, means it's an ideal gas. So anywhere where we have something that's lower than 1 or even greater than 1, which is sort of pretty difficult to do right over there. That's where we deviate from being an ideal gas. So you can see at low pressures, that could be the truth. Right here, here's your critical pressure right there, that's straight line up. We could also see that here is where 1, like right in here, excuse me, right here. Here's a temperature ratio of 1 right in there. It's just below that 1.05. And you can also see that we have a temperature ratio, or reduced temperature of 0.95 that starts to like bend over there. And then here's 0.9, it's constant, and then it comes back and starts to bend over there. So that's how you read those lines. Lastly, just as an overview for logarithms, you'll note that we never get to 0. So you get 0.01, 0.1, and 1, and then 10 right here. So they go in terms of tens. So when we come and take a look at this line, 0.1, this next line over is 0.2, right? So here's 0.1, 0.2, and then there's in between two, right? So here's 0.15 right there, and here's 0.2. And then so here's 0.25, here's 0.3, 0.35, 0.4, 0.45, 0.5, 0.55, 0.6. But now we go 7, 8, 9. So they stopped with the halvesies right in there. So be careful when you're doing this right here that you kind of look through them very carefully, and having a ruler and laying it over this will be very, very much help. Just to as another review over here, try it again right here. Here's 2, 3, 4, 5, 6, 7, 8, 9, and then 10. Right, so here you go. 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5, 5.5, 6, and then they gave up on making the in-between one. 7, 8, 9, 10. And for an interesting thing to take a look at, remember for this scale right here, what we're looking at is 10 raised to the x, right? So this x is what we're looking at right here. So this value right here would actually be, if you will, that's going to be equal to, I'm trying to say it the right way. Yeah, that would be equal to 1 right in there. I think, is that right? I think so, right? So if you take the logarithm of 1, and let's say you take 1, and you take the log. You're going to take the log of it. Oh, you can get 0. Okay. All right. Let me take that back. I think it has to be for a much larger value. I think so. Yeah. Yeah. It should be 10 to the 0. Should stop this video right here because I look like an idiot. No, I think I know what it's talking about. Okay, yeah. If you were going, yeah. So this would be 10 to the 1 right there. Yeah, and this is like 10 to the 0. Yeah, that's right. Okay. So like if you had the larger scale, what I'm referring to, the next thing up right there is going to be 10 to the 2, right? So if you wanted to like find a way to like measure the scale in between these, this doesn't really count for this scale. I'm sorry. I was trying to convey an easy way to like figure out how to find a value in a larger log scale. It doesn't quite work so easily for down here. Just ignore everything I just said. Yeah, that's good. Okay, I'm gonna leave it in here because I don't have enough time to re-record things. The equations of state. I'm just gonna continue on blabbering. The equations of state. This is not something we're going to use, but we could, and there are several variations of this to make an even better correction, or more, instead of looking up on a chart, you could even say that this chart perhaps is developed from these equations of state, but it goes into a little bit more, and I would say that maybe you want to wait for grad school classes where you're going to try to adapt and maybe write a computer code to try to incorporate the compressibility of these. All right, so I am going to, let's see, I have a couple slides left. I think they were talking about the same thing. Yeah, that's off of mine. Here you go. Here's what I was referring to. If you have like C, D, this B and A, I don't know why they didn't put them in alphabetical order, but they didn't. Onto these right here, these are these correction factors that you can place onto them. Sure. And there's various guys right here. So we have van der Waals, Redlick, Kwong, Suave, Hang, Robinson. So, and for these, you actually have to go 2 stages, right? And I'm not even sure what this omega is supposed to be. I don't know. But anyway, it's interesting, huh? That they're going to make even more corrections on top of the corrections. Corrections, these are other corrections besides these corrections. But let's get some practice using them. It's not necessarily easy. So, practice.